for organization of these very interesting seminars. And probably my seminar is somehow not very close to what was heard before, but I think it may be still interesting. So I will talk today about a constructive time delay approach to averaging with application to extremum seeking, and of course extremum seeking with large delays and e-brackets based averaging. And I will conclude my talk and tell about some extensions. So this work was joint work with my recent postdocs, Jin Sheng, who is now in Shanghai University, Yang Zhu, now in Zhejiang University, and Shuifei Jiang. This is on the Dead Sea, by the way. He is in Harbin Institute of Technology. So let us start with classical averaging. So the existing results on averaging that starts from Boголюбов and Metropolsky, and even before, for fixed or more years, they are based on approximations and are qualitative. For small enough value of parameter, everything should work. And so in related control, where oscillation frequencies can be found by simulations only, which may be not reliable. So we present a new time delay approach to averaging with quantitative results, making averaging-based control reliable. And I will remind you the classical results for the simple linear system with fastly varying periodic coefficients here. And I refer to the book of Khalil. So let us assume that A is epsilon periodic, so written in time tau, it is, which is T over epsilon, it is 1 periodic, and we assume that its average over the period, or written like this, A average is Hurwitz. Then, according to classical results, the system is exponentially stable for small enough epsilon. So these are qualitative results, and actually in my Soviet and Russian time, when I was in mathematics, I worked with singularly perturbed systems and with qualitative methods. But when I moved to Israel, to engineering department, because my husband got position on mathematics, I was asked by engineers, okay, it works for small enough values of epsilon, but what is this upper bound on epsilon which guarantees everything? And since that time, I switched to quantitative constructive methods. So if for single perturbed system, these methods and construction of Lyapunov functions was rather natural, for averaging case, it is not the same, because we cannot see in our system something with nominal part which is good, and how to construct Lyapunov function, and we need some transformation. And so this is my first approach, and the main which I will present here is the time delay transformation of this system to have nominal part, which is with good constant metrics and some small perturbations. So do you see any delays in the system or here? Meanwhile, no delays. But if we do backward integration, not from t till t plus epsilon, but from t minus epsilon till t, and we integrate both sides of equation, then we can finish up with differential time delay systems where the nominal part will be what we need. So, I'm sorry. And this was done with, in our first paper with Jin Zheng. So we considered this linear system and we called it with almost periodic coefficients in the sense that the average of A is Hurwitz matrix, constant Hurwitz plus some small norm-bounded uncertainty. So here, under this assumption, we of course assume that A average is Hurwitz. Under this assumption, the average system looks like this, and it is exponentially stable when delta A is small. And actually, there were attempts to construct Lyapunov functions for stability via averaging, but efficient hour bounds these works did not provide. So, how to present our system and how to transform it to time delay differential system. So this is the basic trick. We integrate the left, the x dot, the left side of the equation, and of course we finish up with this finite difference, but we don't want to present it as finite difference. We want to present it as differential, as derivative of xt and something small. And this something small looks like this. Why it is small? Because if x dot of the order of 1, then here we have order of epsilon, and here we have additional epsilon divided by epsilon. So altogether, this is of the order of epsilon. And this trick actually I borrowed from my previous papers on artificial stabilizing delay, where I also use the so-called neutral type transformation. We will finish up with neutral type system. So the left-hand part is like this, and in the right-hand part, we have just integration of what we have, of course, divided by 1 over epsilon, and we add and subtract xt in the present time. So what we have here, this integral multiplied by xt gives us exactly, by our assumption, the nominal part with constant Hurwitz matrix A average, but the difference xs minus xt we present as it is standard for in time delay analysis as integral of x dot. And this will be also of the order of epsilon because this, if x dot of the order of 1, because this interval is of the order of epsilon. So finally, we finished up with such system, G actually here instead of x dot should be the right-hand side, A multiplied by x. So all this gives us distributed delay term, and this is the so-called neutral type system in the form of Hill, when we have derivative of x minus past values of x. And this term is of the order of epsilon. So, of course, this system might be not equivalent to the original one, but all the solutions of the original one satisfy to this equation. So, if this system is stable or ISS or has some L2 gain bounds, then the same we can claim for the original system. And now we have to analyze this time delay system. So here we can apply, and this is what we have done in our papers, Lyapunov-Krasovsky method, which leads to LMIs for upper bound on epsilon preserving stability. Note that epsilon here means upper bound on the delay. And the Lyapunov-Krasovsky, which we use, this part, the main part, this is due to the left-hand side of the equation. We put it here. But when we differentiate this, we have to create minus g squared terms and minus y squared terms, and in order to make v dot negative. And to do this, we use the following construction, which after differentiation and application of Jensen inequality gives us what we want. And we want the following, that B is positive in this sense. And V dot plus 2 alpha V is negative for all epsilon which are less or equal than epsilon star upper bound. And so alpha is the common decay rate. So see, in our first paper, we additionally proved that this difference equation is stable, which was classically assumed to be for neutral type systems, but later we understood that we don't need this because our construction guarantees this low bound positivity in terms of x of t. And so these two conditions guarantees exponential stability of x at time t. And the examples which are very important examples, classical ones, this is the so-called Kapitza pendulum, where we can stabilize it in the vertical position by using fast vertical oscillation with small amplitude. And so the resulting system is given like this, linearized in the vertical position with this averaged matrix. This is example from Khalil. And so from Khalil, we can conclude that if gamma square is like this, then for small epsilon, the pendulum is exponentially stable. But how to find upper bound on epsilon which corresponds, which preserves this stability? This can be found from our LMIs, and this is decay rate, which is good for all epsilon small or equal than this upper bound. Of course, this is very conservative. And now we under construction are much more efficient results, and we have essential, we may achieve essential improvement of this by modification of transformation and Lyapunov function. Okay, sorry. Another important example is stabilization of switch system by fast switching. Well, it is classical result that if we have two unstable system with a convex combination which is stable, then by fast switching like this, which in the average gives us exactly the convex combination which is stable, we can stabilize the system. But how to find the upper bound on epsilon, especially if we can treat uncertainties, global ellipses, non-linearities, or even local ellipses, because we have direct Lyapunov method. So in this example, we had also achieved some reasonable upper bound on epsilon, and from numerical simulation, epsilon is even not small, but our method, of course, works for small values of epsilon. So because we have exponential stability conditions, we can extend it to ISS with fastly varying or constant B here, to systems with time varying but small time varying delays for persistently excited stochastic systems. And recently with Denis Yefimov, we have considered ISS with respect to some average disturbances for input affine nonlinear systems. And on the coming CDC, we will present a new transformation, non-delayed transformation with Lyapunov functions and some improvements in examples. And this was done together with my recent PhD, Rami Katz, who had presentation on this seminar, and Frederic Massa. And I will just mention that we had some applications of this method to power systems and to Brocket's problem. What is this problem? That we consider, for instance, such linear system, and in some cases we are interested in static output feedback. But in some cases, when where static output feedback does not work, it appears that fastly varying gain here may stabilize the system. And this is known, but known either in the qualitative sense or by numerical simulations. And we give theoretical proof for this. For instance, for such system, we consider the so-called square wave dither plus minus 1, which is fastly varying, and we have full solution to the Brocket's problem, in the sense that we have upper bound on epsilon. And now we move to extremum seeking. And our first result on extreme seeking was with Yang Zhu, and he made this beautiful picture. So extremum seeking is the method for real-time model-free optimization. And it started 100 years ago in application to the power transfer of electric tram car by LeBlanc. This is the origin. And I will mention just important seminal result by Miroslav Kristich, where he gave general rigorous proof for a general class of extreme seeking systems. And this is Tiago Oliveira, who first told me about extreme seeking when I visited him in Brazil, and told that, well, he worked with Miroslav with extreme seeking in the presence of large delays, but he wanted to apply my methods for network-based control, for sample data control, to extreme seeking. And I asked him, so how does it work? And he told, this is based on averaging. And we use the paper by Jack Hale on averaging. And in this paper, there is only constant delay. So I told that something is missing. If you want to add fastly varying, time varying delays, you need some justification. And this gave me also motivation, and of course, Slav in our discussions, and that's how I switched to extremum seeking. So what is the problem here? I will start this. Well, these are very recent results. Our first paper appeared just in 22, and there is a lot to be done in this direction. So let us, for simplicity, start with one big quadratic map like this. And we know just the sign of the so-called Hessian. And so our objective, by measurements of y only, we want to find algorithm that brings our state to the extremum point and our map to extremum value. And so, of course, if everything is unknown, we cannot talk about quantity, but in many applications, we can consider gray box model where something is known about your system. For instance, you even may know your map, but you have GPS denied environment in the multidimensional pieces. You cannot measure your state. Then you cannot use gradient of this map, which would be used if everything is known. Yes, this is classical gradient descent method to find the optimal value. So we consider this gray box model, and we assume some uncertainties in all the parameters that we have. And this is the classical gradient-based extreme seeking algorithm, which is adaptive algorithm. So we construct the real-time estimate theta hat of theta star, and we want to approach to it asymptotically. And this is the algorithm. So we don't know the direction. So we add some fastly varying dither, and we try all the directions. And our control law static output feedback looks like this. So here we have fastly varying dither. And this is the system for which we want to have some practical stability if theta hat converges to something close to theta star, and A is small, then we approach to theta star. And now how to analyze this? So we present the estimation error like this, and then it is governed by this ODE. And if we open the brackets, we finish up with this nominal part and these terms with average which is 0. So after averaging, this gives some small error in the convergence to 0. So we choose, with the knowledge of the sign of the Hessian, we choose appropriate sign of K, and then this is exponentially stable, and then we conclude, and this is really a result of Miroslav, that the estimation bound is upper bounded by something exponentially converging to the extremum point plus small for term for high frequency oscillation and plus another small h. But how to find the bounds on this in order to guarantee all this? And we can also find actually the ultimate bounds on this. Unfortunately, somebody is cleaning. I don't know if you hear me. Okay. Okay. So we denote omega as 2 pi divided by epsilon, and epsilon is dither period. And then we apply our time delay approach, and we present our extreme seeking system in the form that we have seen: nominal stable part and small perturbation terms. And we can further use here what is the difference, that now we have nonlinear case because Y2 is nonlinear. So here we have semi-global results, assuming that the initial condition starts from some sigma 0 neighborhood. We find the bound on theta, which is theta tilde, which is less than sigma, and then we can find upper bound on epsilon, which preserves everything. And these were our first semi-global results. So theoretically, we can start as far as we want from the unknown extremum point, and can have some upper bound on epsilon, but to have something bound which is not 0, we have to be closer to the extreme point, which is natural. And another method is the so-called bounded extremum seeking, which was introduced by Schenker and Kristich. And here this part is bounded, and this method is more robust. For instance, it is not sensitive with respect to this constant value in the mapping. It works the same and gives the same results for any F star, which is good. So here the existing results use the Lie brackets based averaging and approximations, another class, because we cannot use the classical for this, we cannot use directly the classical averaging because these terms are of the order of 1 over square root of epsilon. And by using time delay transformation, it works absolutely the same for Lie brackets. And Miroslav was surprised how simple it looks like. And we finished up with such a system, basically the same kind. And we have also a semi-global result with ultimate bounds. And this is the example scalar static map. And we consider classical and bounded extreme seeking. And so for classical, we assume uncertainty of F star of the map. And for bounded extreme seeking, we have the results for all F star. Of course, here for classical, we have a smaller upper bound than a larger upper bound. On epsilon, it means that this allows low frequencies here, but this is more robust. And this is the initial interval. We start from one neighborhood of the extremum point, and these are the ultimate bounds that we have found in our very first paper. Everything is now improved. And our next step was done with Yang Shu and Tiago. Tiago's dream came true. We considered here sample data, implementation with additional constant delay. This is a square wave dither, and we have managed with this case by the same more or less steps, of course, with some complications because of additional delay. And so after our time delay transformation, we finished up with such system and these additional disturbances terms, and we proceed with SS-like stability analysis. And this is the example, I think, which is perfectly suited to our case. This is GPS denied 2D vehicle control from Schenker and Kristich, where we want to arrive at a region by measuring the distance only. So the map is known here, but gradient is unknown because we don't know X and Y. And that is why we apply this extreme seeking, and we have bounds on epsilon and on additional delay. And epsilon is also our sampling period, yes, and frequency period. Okay, so further with Ruife-Young, we extended these results to ND static maps, and we have suggested some improved analysis. So here we assume, as previously, we know the sign of this Hessian matrix, assume that it is positive, definite, then we have minimum point, and we also assume that theta is from the known ball, but results are semi-global, as I explained to you previously, and Q is upper bounded, and H is presented as some nominal known value and additional non-bounded disturbance. And so we consider the classical gradient-based extreme seeking with dither signals S with different frequencies here and M with different frequencies. And the adaptation gain is, which is K matrix, and by matrix we choose as diagonal matrix with negative Ki, such that Kh here is Hurwitz. It is always possible to do this. And here we finish up with this presentation, time delay presentation. And in this paper, we do the next step. We denote IZ this difference, and then we finish up already with ODE and small disturbances. And if we find the bound on Z and G, we can find the bound on the estimation error is written here. And since this is linear system, we can with known KH here up to uncertainty, we can use variation of constants formula, and we don't use Lyapunov-Krasovsky that our reviewers do not like because they don't deal with time delay systems. And we have much simpler conditions, and in most of the examples, more efficient ones. So, by the way, this will be presented on CDC 23, and in the same 1D example, for instance, instead of uncertainty, which is very small in H, we can allow a huge uncertainty in the Hessian and achieve the same upper bound on epsilon, which is fine. And we have also smaller ultimate bound, and we applied this to 2D vehicle in GPS denied environment and got much better results. So these are improvements. And the challenging thing is, of course, for us is time delay. And in our IFAC paper, we followed the results by Oliveira and Miroslav and authors, where we considered this quadratic map. And in the measurement, we had constant, but actually, theta is multi-variable, and in each variable we have distinct delays, and this is also challenging, but this is simplified formulation. It does not correspond to an input, actually. It is some generalized map with different delays, which was considered in the previous literature. But in our journal version, we consider a real situation with distinct input delay, where analysis becomes more challenging. Okay, so meanwhile, in this formulation, we could apply the same extreme seeking algorithm, and under assumption of some known nominal values, we can finish up with such a system. And actually, we can proceed with variation of constants formula, but now instead of exponent of matrix, we use here the so-called fundamental solution to time delay system. which means solution of this system with initial condition, which is 0 before 0 and identity in 0. But this gives us very, if we use, for instance, LMIs to find this exponential bound on the fundamental matrix, we finish up with very conservative results, and we would like to have as tight bounds as possible. And it appears that the tight bounds on the fundamental solution with the not just bound, tight exponential bounds on fundamental solution have been given in the case of scalar system. I will show them later. And so our first step is to diagonalize the nominal part of this quadratic map. And we have suggested orthogonal transformation, which preserves the norm of the state and of norm-bounded uncertainties. And we finished up in new coordinates with such a map with diagonal matrix H. And here we have known nominal part and uncertainty. And now we use the same algorithm as I showed you, but for the transformed system, and finish after additional change in our time delay transformation. We finish up with this system. And now here we have diagonal matrix KH, and this is the variation of constants formula where X capital is the fundamental solution matrix. And here is the result about the tight exponential bound, which we found in the book by Agarwal and co-authors, and it is based on the positivity non-oscillations of the fundamental matrix, which are preserved provided this bound holds. Then, if for instance, given di, known di, and known h, this is coefficient in Hessian, we can always find the gain ki such that this product is less than 1 over e. Then the fundamental matrix does not change the sign, it preserves the positivity, and this is the decay rate, which is the same as decay rate for non-delayed case. This is, I think, fantastic result, because usually, okay, when you have no delay, you enlarge the gain in order to have a better decay rate. But if in the presence of the delay, it decreases the value of delay. So how to find trade-off? And if we have this bound, then the decay rate is preserved. And based on this, we have some nice conditions in the example from Thiago and Michael Malesov with Miroslav, and we have bounds in the presence of norm-bounded uncertainty and ultimate bound, which is nice. And now with Jinzheng, we have considered also the so-called input affine systems. And here we have this high gain, 1 over square root of small epsilon, and UI has a zero average, it is epsilon periodic and piecewise continuous and bounded. And we assume F0 continuous and locally Lipschitz in X, and Fi C2 with good bounds on all these functions. And we also have considered the disturbance from L infinity. And a classical Lie averaging, Lie brackets approximations. In Lie brackets approximation, people use forward integration and finish up with integral equations. And then they find the results based on integral equations. I think the advantage of our approach that we finish up with differential equation where we know much wider tools for stability and performance and ISS analysis. So the average system in this case is given in terms of the so-called Lie brackets, which are given like this, and with beta coefficients given like this. And so objective approximation-free analysis with quantitative and accurate qualitative bounds. So actually in our already in our first paper on bounded extreme seeking, we gave not just the first quantitative results, but we gave precise ultimate bound in terms of the parameters of the system, which has not been given before by using Lie brackets approximation. And so in this case, surprisingly for Miroslav, by using this G, we finished up with the same structure. Of course, it is more complicated. We have more terms, small terms here, but the nominal part is given by a Lie bracket system. And so we applied this approach to the Nussbaum problem in some particular case where we have, for instance, linear uncertain system, but we don't know the sign of B0. And we apply the bounded extreme seeking, but here we extend it to some small fast varying delay. And we can manage also with this case by using the Lie brackets result that I have shown you. We finish up with such average system, and if there exists case such that this is stable, then we can manage and we can give a complete solution in the sense that we can give upper bounds on epsilon, which guarantees practical stability. I think so these are the examples. We considered the scalar case where B0 may be either plus or minus 1, and we have chosen these tuning parameters, and the average was given like this, and we achieved delta decay rate like this. And in the more interesting two-dimensional example, we have chosen matrix A0 like this and B0 plus minus 1, 1. And we have also, these are the results by various methods. By the way, of course, we have improved our result, our first result, by by bounded extreme seeking, but for instance, using variation of constants formula, in this case, gave worse bounds than by using Lyapunov-Krasovsky in our journal version. But we have some better case where automatic result did not work, and here we had some epsilon. And now for the 2D example, our improved modified analysis with variation of constant formula give much better result here. And I think I will mention also some current and future work. So we have considered with Shui-Fei-Yang the extension to discrete time extremum seeking, which is under review now, and to dynamic maps in CDC with Yang-Zhu, and non-quadratic maps with some journal extension, and stochastic measurements with Shui-Fei-Yang and his PhD student. And so to conclude, the Dandeli approach provides approximation-free analysis via averaging, allows efficient quantitative and accurate qualitative bounds for extremum seeking, and opens the doors for delay stochastic systems, PDEs. I just want to mention that, for instance, in the book by Tiago and Miroslav, they mentioned some results for time varying delays to be justified later on, because there are no existing results which are applicable to their case. And if you use this time delay approach, you can finish up with justification and with what you need. So I think this is a nice approach, and thank you very much.